Good day everyone. Today we will be talking about probability of independent events. So in this lesson, you will illustrate independent events, differentiates dependent events from dependent events, finds the probability that one event and another event will occur, and solves problems involving probability of independent events. So let's try to explore this lesson and understand independent event and dependent event. Supposedly we have here, state whether the result of the first event affects the second event. Number 1, studying hard, getting a high grade. Number 2, first event is eating a lot. And the second event is gaining weight. Number 3, playing computer games is the first event, and the second event is submitting all assignments and projects on time. Number 4, tossing a coin is the first event, and the second event, which is rolling a die and getting a 6. Number 5, the first event is attending a singing lesson, and the second event is raining today. Sometimes the result of one event affects the probability of the second event. For instance, if you study hard in number 1, the probability of getting a high grade increases, right? Similarly, if you eat a lot every day, it increases the probability that you will gain weight. Number 3, playing computer games may affect your chances of submitting all assignments and projects on time. However, the result of tossing a coin does not affect the probability of getting a 6 when a die is rolled. Also, attending the singing lesson in number 5 does not affect the probability that it will rain today. When knowledge of whether an event occurs affects the probability of a second event, the events are said to be dependent. But when the knowledge of the first event does not affect the probability of the second, the events are independent. So numbers 1, 2, 3 are dependent, while numbers 4 and 5 are independent events. Let's have example number 1. Decide whether the two events are dependent or independent. Letter A, rolling a 5 on a consecutive turns in a game. Letter B, drawing a card from a deck of cards, returning it and drawing another card. Letter C, drawing a card from a deck of cards and drawing a second card. Letter D, working hard and achieving your goals. Let's try to solve letter A. Rolling a 5 on consecutive turns in a game. This event is independent event. Why? Or these are independent events. The result of the first roll does not affect the result of the second roll. Right? Letter B, drawing a card from a deck of cards, returning it, and drawing another card. Letter B is also independent events. Why? Since the first card is returned to the deck of cards, the probability of the second event is not affected. Letter C, drawing a card from a deck of cards and drawing a second card. These events are dependent events. Why? In this case, since the first card was not returned to the deck of cards, the probability of the event is affected as there are now only 51 cards in the deck of cards. Letter D, working hard and achieving your goals. These events are dependent events. Why dependent? Working hard increases your chances of achieving your goals. Now let's try to explore the probability of independent events. How do you solve it? Supposedly we have here red and blue marbles. A bag contains 2 red marbles and 1 blue marble. Wilfredo draws a marble, then returns it to the bag. He draws a second marble. What is the probability that the first marble is red and the second marble is blue? So let A be the event that the first marble is drawn is red. So what is the probability of the red marble? So we have 2 red marbles over 3 marbles in all. So 2/3 is the probability of A. Let B the event that the second marble drawn is blue. So the probability of B is 1/3 because there is only one blue marble. Note that event A occurring has no effect on event B occurring, and vice versa since the marble is returned to the bag after the first draw. Thus, these events are said to be independent. Let us show these example or the possible outcomes in a tree diagram. So we have here the first draw, the second draw, and the outcomes. So the first draw, it could be red, or blue because there are 3 marbles in the bag, right? So in the second draw, it could be red, blue, and so on. So the outcomes here, we have red, blue, red, blue, red, blue. So there are 9 outcomes. So let A be the event that the marble drawn is red, and let B the event that the second marble drawn is blue. So what are the outcomes or the sample spaces of A? So we have, since A is red, the first marble is red. So we have red, blue, red, blue. So there are 2, 4, 6 in all. While in letter B, event that the second marble drawn is blue. The second marble, look at the second letter, it's blue. So red, blue, blue. There are 3 possible outcomes. So when we have A intersection B, what do you mean by A intersection B? Getting a red on the first draw, replacing the marbles, and getting a blue on the second draw. So we have only 2. The first draw, which is red, and the second draw, which is blue. So red, blue, and red, blue. So there are 2 sample spaces or possible outcomes. So what is then now the probability of the intersection of A and B? When we say then the probability of A intersection and B, that means that responds to the question, what is the probability of getting a red on the first draw, which is A, replacing the marbles, and getting a blue on the second draw, which is event B? So we have here, since there are only 2 intersection of the 2 events over the possible outcomes, which is 9, so the probability of getting a red on the first draw and getting a blue on the second draw is 2/9. Or let's have this another example. The probability of A is equal to 6/9. Why? We will just count how many are the sample spaces there, RB, and so on. So there are 6. So over 9, the total outcome, so we will reduce, so that's 2/3. And the probability of event B, which is the second marble drawn is blue, that is 1/3, right? Or 3/9, or 1/3. So in getting the probability of A and B, we will just have to multiply probability of A times the probability of B, which is 2/3, times the probability of B, which is 1/3. What is 2/3 times 1/3? That is 2/9. We have the same answer, right? Thus, the probability of getting a red marble on the first draw and a blue marble on the second draw is 2/9. We will just simply multiply the two probabilities. The result is the same as P, or the probability of the intersection A and B, and this suggests the following theorem: the probability of independent events, which is the probability of A and B, is equal to the probability of A times the probability of B, where A and B are independent events. Again, independent events. the second event doesn't affect the first event. So we have example number 2. A die and a coin are tossed. What is the probability of getting a 6 and a tail? 6 and a tail. Let's check if these events are independent events. So getting a 6 and getting a tail. Does it affect the getting a 6 and... No, it does not affect. So these are independent events. So the sample space for this experiment is we have 1H, 1T, 2H, 2T, 3H, 3T, and so on. And let A be the event that the die comes up 6. That's the first event. So we have here 6H and 6T. So we have 2, right? And let B the event that the coin lands tails. How many are there? So we have 1T, 2T, 3T, 4T, 5T, and 6T. So there are 6. So the intersection of A and B, event A and B, is only 6T. When we say intersection, what is the common of the two events? We have 6H. 6T. So we have 6T. So that means the probability of A, which is how many are the event that the die comes up with 6, we have 2, 6H and 6T, over how many are in all? 12. So 2 over 12, that is 1/6, right? And the probability of B is 1, 2, 3, 4, 5, 6. There are 6 events that the coin lands tails, and there are 12 in all, so 1/2. So what is now the probability of the intersection A and B? So we'll just multiply 1/6 and 1/2, that is 1 over 12. So the probability of the intersection of A and B or is equal to 1 over 12. 1, it's only 60, right? The intersection of U and B, that's only 60. So that means the probability of getting a 6 in a tail is 1 over 12. Example number 3. 2 dice are rolled. Find the probability that a number 1 is rolled on the first die and a factor of 6 is rolled in the second die. These two events are independent. The probability of A1, the first event, in the first die is 1 over 6. In the second event, which is, or second die, a factor of 6. How many are the factors of 6? We have 4. What are those? 1, 2, 3, and 6. Those are the numbers which are factors of 6. So 4 over how many in all? 6, so that is 2/3. Right? So we will just multiply the two events, 1/6 and 2/3. So the probability of 1 in the factor of 6, we have 1/6 times 2/3 is equal to 2 over 18 or 1/9. So the probability that a number is 1 is rolled in the first die and a factor of 6 is rolled in the second die is 1 over 9. Example number 4. A card is drawn from a deck of cards, then the card is replaced. The card is reshuffled and the second card is drawn. What is the probability of a 3 on the first draw and a 4 on the second draw? Knowing that a 3 is drawn on the first draw yields no information about what occurs in the second draw, since the first card is replaced and the deck is reshuffled. So these events are independent. So what is the probability that it is a 3? So there are 3 cards. There are 4 cards which is a 3, which is 3 spades, 3 clubs, 3 diamonds, and 3 hearts. So there are 4 over 52 cards in a standard deck of cards, so 4 over 52. And also there are also 4 cards, which is 4 spade, 4 clubs, 4 hearts, and 4 diamonds. So we have 4 over 52. Since it is independent, we will just multiply the two probabilities. So 4 over 52 times 4 over 52, that is equal to 16 over 2704, or 1 over 169. Thus, the probability is 1 over 169. Number 5. A jar contains 4 white balls and 1 black ball. A ball is drawn from the jar and returned before the next draw. What is the probability of drawing 3 white balls? Solution. Since the event of drawing a white ball on each of the 3 draws is independent of the other draws, so we will just multiply again. So the first probability, which is a white, we have 4 over 5, right? And the second draw is also 4 over 5 in getting a white ball. In the third draw, it's also 4 over 5 because the balls are returned, right? So 4 over 5. So we will multiply the 3 probabilities. So 4 fifth times 4 fifth times 4 fifth, that is equal to 64 over 125, or what is it? The probability is 64 over 125. Example number 6. Suppose A and B are independent events with the probability of A is equal to 0.4 and probability of B is 0.2. Find the probability of A intersection B, or A and B. Since A and B are independent events, so the probability of A is 0.4 and the probability of B is 0.2, so we will just multiply the two events. So 0.4 times 0.2, we have 0.08. Thus, the probability is 0.08. Example number 7. If there is 60% chance of rain on Saturday and 50% chance of rain on Sunday, what is the probability that it will rain on either Saturday or Sunday? The event that it will rain on Saturday and the event that it will rain on Sunday are inclusive and independent. Since the probability of it will rain on Saturday is 0.6 or 60%, and the probability of Sunday, which is 0.5, so the probability of Saturday or Sunday is equal to the probability of that it will rain on Saturday plus the probability that it will rain on Sunday minus the intersection of the two, which is the probability of Saturday and Sunday. Thus, probability of it will rain on Saturday is 0.6 plus on Sunday, which is 0.5, minus the probability of the intersection of Saturday and Sunday, which is 0.6 times 0.5. So, what is 0.6 plus 0.5? Is 1.1, and minus 0.6 times 0.5, this is 0.3. 1.1 minus 0.3, that is 0.8. Thus, the probability that it will rain on Saturday or Sunday is 80%. Example number 8. Stephen Curry, the all-time free throw percentage leader of National Basketball Association, or NBA, as of March 27, 2021, has a free throw shooting percentage of 90.72%. If he attempts 4 free throws over the course of the game, what is the probability that he will miss at least one of them? First, find the probability that he makes all four. Assume that each free throw is an independent event. So we have here makes all four. Why it's raised to the power 4? Because the first event is 0.9072. The second shoot or free throw, it's 90.72. The third throw, 90.72%. And the third throw, 90.72%. So that is why it's raised to the power 4. So 0.9072 to the power 4. That is equal to 0.67735. And that is the probability that he makes all four. This is the probability that he makes all four free throws, right? So how about making all four is complement to the missing at least one? So what is the probability that he will miss at least one? That is 1 minus, it's a complement, so we will just subtract 1 minus the probability that it makes all four, that is 0.67735, which is equal to 0.33265. So that is the probability that he will miss at least one of the free throws is about 32%. Where did we get 32%? We will just multiply 0.32265 by 100%. That is 32.265. So that is about 32%. Let's have example number 9. This is an enrichment about the probability using permutations and combinations. Supposedly, OLET has the options of selecting 3 novels for a literature course. The book lists consist of 10 classics and 5 contemporary novels. Find the probability that all novels selected will be contemporary novels. To select 3 from 5 contemporary novels, we must find first the combination of 5 taken 3 at a time. So why combination of 5 taken 3 at a time? Because there are only 5 contemporary novels and he will select 3 novels, right? So we have here 5 factorial over 3 factorial times 5 minus 3 factorial, that is equal to 5 times 4 times 3 factorial all over, what is 5 minus 3? That is 2 factorial. Then 3 factorial over 2 factorial, so we will just cancel 3 factorial, that is 5 times 4 over 2 times 1 is 20 over 2, that is 10. So there are 10 combinations. Since OLET has to select 3 novels from different or the 15 novels in the list, so the total number of outcomes in the sample space is given by a combination of 15 objects taken 3 at a time. So that is 15 factorial all over 3 factorial times 15 minus 3 factorial. When we simplify that one, that is equal to 455. Thus, the probability of selecting 3 contemporary novels is 10 over 455. Where did we get 10? That is probability of from 5 contemporary novels over the probability of 15 novels, which we select 3 novels. So 10 over 455 or 2 over 92, which is also approximately equal to 0.022. Example number 10. A pet shop has 5 Ascol and 3 Pomeranians. If a customer buys 3 puppies at random, find the probability that the customer will select 2 Ascol and 1 Pomeranian. There are 5 combinations of taking 2 at a time ways to select 2 Haskell's from 5 Haskell's, right? So 5 factorial over 2 factorial times 5 minus 2 factorial is equal to 10. Since there are the combination of 3 taken 1 at a time ways to select 1 Pomeranian from 3 Pomeranians. So the combination is 3 factorial over 1 factorial times 3 minus 1 factorial. When we simplify that one, that is equal to 2. Hence, there are 10 times 2 ways to select 2 Haskell's and 1 Pomeranian. In these topics, AND generally means to multiply. So, there are 20 ways to select 2 Haskell's and 1 Pomeranian. So, we have here, there are 8 combinations taken 3 at a time ways to select 3 puppies from 8 puppies. So we have here 8 factorial over 3 factorial times 8 minus 3 factorial. When we simplify that one, that is 56. Thus, the probability of selecting 2 Haskell's and 1 Pomeranian is 20 over 56, or we have approximately 0.357. Example number 11. A combination lock shows 10 digits. Find the probability that if the combination to unlock the lock consists of 3 digits, it will contain digits 1, 2, and 3. Note, a combination lock is actually a permutation lock since the order of the digit is important when unlocking the lock. Repetitions are not permitted. The number of ways 1, 2, 3 can be used is the permutation of 3 taken 3 at a time is equal to 3 factorial over 3 minus 3 factorial, that is equal to 6. Right? The number of ways to select 3 digits from 10 digits in order is equal to 10 factorial over 10 minus 3 factorial, which is equal to 720. Hence, the probability of selecting 1, 2, and 3 in any order is 6 over 720, or 1 over 120, or approximately 0.008. So reflection. Instead of saying, I'm not good at this, try thinking, I can be good at this. Instead of, I give up, try thinking, I will work harder. Instead of, it's good enough, try thinking, is this really my best work? Instead of, this is all that I can do, try thinking, I can always improve. Instead of, I just can't do this, try thinking, I will learn to do this. Thank you and good day.